Hi, today's video we are going to review the concept of low-shear bending diagram by looking at another example. Not only we review how this process goes, and I'm introducing the new element through this example. So, example 2. We'll have a simply supported beam. You have a pin support and a roller support. However, this time we don't have a concentrated load in the middle. We're actually going to have a bending moment right in the middle, M0. Okay. The similarity between this one and the previous example we did is they have two sections. The first section is going to be when x is equal to 0 over half L. The second one will be x is greater than half than less than L. Okay. So if we were looking at the first section, we're going to cut randomly anywhere between the first section. So we can make a cut here in this blue line. So when we make a cut, we're going to draw our first FBD. Then we will have this section right here to the left. Let's go ahead and put all the forces on this FBD. So first of all, we understand there is going to be reaction support on both, right? But we haven't solved that yet. So we're going to go back to this entire FBD. I'm going to call it to 0. To solve these forces. And we're going to call this A and this B. Let's go ahead and solve A first. If we want to solve A in one step, we're going to do moment about B. Okay, so we'll have A times moment of arm will be L entire length. And that's clockwise, so that's negative. Then we'll have this external moment M0 right here, and that's clockwise rotation. That's going to be negative M0, and that will be our moment equation. And be mindful what we are solving. We are solving this A because this M0 is given. That's the external moment. So this force at A is going to be equal to negative M0 over L. Okay, if we get that, we're going to using summation of the forces at y direction equal to 0. We'll have this A plus B equal to 0. And since A is already found, so B will be just equal to M0 over L. Okay, so we got our external reaction support. Once we know that, we can translate that into our FBD number 1 here. So this will be ML over L. However, since there's a negative sign in front of it, so the true direction is actually, instead of going up, is actually going downward, right? So the force here at A is M0 over L. Then at what we cut, we're going to have our internal loading bundle. As usual, we'll have our normal force, make it tension to be positive, and shear to make a clockwise rotation V, and bending to make a happy face. So we are going to solve all three of them. So first, you can quickly calculate it. Calculate N will be equal to 0. That's the only horizontal force. Then forces at y direction, we will have negative ML 0 over L. That's going to be your external force right here. Then minus V, because this V is going downward. And that equal to 0. Then we get V is going to be equal to negative M0 over L. That's our shear. Then the last thing to solve is our moment. So we're going to do moment about where we cut. And we have M0 over L. This is external force right here. And that rotating about what we cut, that's going to be what's the moment of arm again for this one? That's right, that's going to be x. So because it's an analytical approach, you randomly cut, that's going to be expressed as x instead of a specific number. So times x, and that's counterclockwise positive. Then we're going to have this m, internal bending moment you are solving. This is counterclockwise, so it's going to be positive in the equation. And you got m. You're solving. Again, be mindful what you're solving. You're solving this internal bending moment, m. That's m gonna be equal to negative m naught over L times x. That's the expression for the bending moment. Okay, so we're down the first half of the beam. As we predicted, the second half of the beam is going to have a different expression for internal loading. So we're going to analyze this part. So we're going to make a cut. This time we're going to cut in the second half randomly anywhere. If we cut right here. So we're going to draw our FBD number 2. So in this situation, you have a choice to look at the left section or right section. Obviously, for this problem, the right section will be the winner. It's easier. So we're going to have force at B, which you already calculated. That's reaction support. It's m naught over L. And at this yellow line where we're going to put our internal loading. So to make this entire section to be in tension, so that would be going to the left for normal. And for shear, to make the entire section clockwise rotation, so this is going to be going up. So that's our V. And to bending, to make a happy smile, M here. So you already know N has to be equal to 0. And the forces at Y will have this V going up, so it's positive. And this m naught over L is going up as well, positive, equal to 0. Then what we calculate is going to be V equal to negative ml over L. So bracket this answer. The next thing we are solving is moment. We're going to moment about where we cut. And then we'll have this m itself. It's clockwise rotation, right? So if it's clockwise, it's going to be negative m. Then we have this force, m naught over L, and times. Okay, so this is an interesting point where we are now. What is going to be the distance for that? Because that's our moment of arm. Okay, so if you are going to look at translate this information to this entire FBD is basically that. That's going to be our question mark. What's that then? Okay, so let's look into it. Remember, where we cut is going to be random, and that's going to be expressed as x. So if we were drawing this again, which means start at point A, where we cut this yellow line, that's going to be our distance L. Because this x is in between this range. Do you agree? Because it's between L over 2 and L. So what is this question mark right here? Be aware this entire length is L. So this question mark right here will give us L over a minus x. So that's where we need to be careful about this one. So it's times L minus x. So that's something new for this problem. And we have that. You're thinking about the direction. So this is going to rotate. For this force, rotating about where you cut is going to be counterclockwise. So that's going to be plus. And all those going to equal to 0. Again, what you're solving, we are solving this m. So m is going to be equal to m naught over L, L minus x. So we want to simplify you would get m naught 1 minus x over L. So that's our expression for moment for the second half. Okay. So let's summarize. You know what we're about to do. We're going to put all those in the load shear bending diagram. So we're going to draw our 3 tiers. First tier being our loading. And we have a moment right in the middle. We also calculate the load at A being this value, and it's negative, which means the true direction is going downward with m naught over L, and at this last point it's m0 over L. Okay, that completes load. Now for the shear. So since it's 2 sections, for the first half, we're going to come back to use this equation. And second half, we're going to use this equation right here. And you realize they're the same, so they are all equal to negative value. And it's a constant value because it's equal to m0 over L. And both are constant, so that gave us the value for that. That's our shear. The last tier is our moment. For our moment, the first half of the beam will have this expression for bending moment. And thinking about how do we draw this. A good procedure to do is exactly what we did last time. We are going to put those beginning and end point. So beginning point is 0 and end point is L over 2. And when we plug it in, our m is going to be equal to 0 for x equal to 0. And when x equal to L over 2, that gives us negative m naught over 2. So that will define the beginning point as 0, the final point as negative m naught over 2. And again, look at this equation. It's certainly a linear equation, so we know it's going to be a straight line connecting those 2 points. And our slope, based on this equation, you can tell it's going to be negative m naught over L. It's negative because it's decreasing. So for the second half, we'll have this equation. And we will do the same thing. Plug the beginning point and end point. Beginning point, this starts L over 2. End point is L. And when you plug it in, your m equals, when you put x equal to L over 2, I believe the answer will give us to be that value. And when you plug x equal to L, that will be giving us m equal to 0. So we now know the beginning and end point for the second half of the beam. The first beginning point is m naught over 2, and end point is 0. And again, look at this equation function. It's a linear, so it's going to be a straight line as well. And what will be the slope? The slope for this will be negative m naught over L by looking at this, right? This equation, that's going to be our slope. So what happens between this point and this is the same point. So basically, it's just jump upward. And then you got this bending diagram. Okay, what does this tell us is at this point, first half, the bending decreasing to a negative value. And then second half, it's completely changing the direction and decreasing from m naught over 2 to 0. Okay, and again, as a structural engineer, what you care about is the maximum bending. And this maximum bending is going to be at this point, regardless it's negative value or positive value. It's just a direction. You care about the magnitude, so the magnitude is m naught over 2. And that is happen at right in the middle as well. Okay, so that finished the example 2 using those shear bending diagram. All right, bye now.